In a recent video, we talked about how simple the binary system is to use, but we did not go in depth as to why or how the binary system physically operates in computers. Numbers are physically stored in computers as a combination of the presence and absence of electricity. For example, the particular combination 101 represents the number 5 in binary. Each 1 is physically represented by the presence of electricity, and each 0 is represented by the absence of electricity in certain locations in a circuit. In order to perform calculations on these numbers, which is basically the extent of what computers do, we need to compare them to each other. This is done using a transistor. What is a transistor? Think about a light switch for a moment. Use an input to make a connection. In other words, the mechanical movement of the switch results in completing the circuit. Imagine this same switch, except it doesn't take mechanical input, it takes an electrical signal to control it. Oh, and it can also switch billions of times per second, and its size is on the order of nanometers. That is a transistor. Clearly, we've spent a great deal of time engineering such devices, so why are they so important? Well, because it's a switch, you can use it to add or remove electricity from certain parts of a circuit. We can use this ability to perform logical operations, and build upon this logic to even perform complex calculations. But before we get ahead of ourselves, we should probably take a look at one first. This is the symbol for a certain type of transistor called a bipolar junction transistor. And this is what it looks like. The actual silicon within this large plastic package is so small, you'd probably not be able to see it if I open the package. But you can see that it has 3 terminals called the collector, emitter, and base. If current is flowing into the base, then electricity is allowed to flow from the collector to the emitter. If current is not flowing into the base, then flow from collector to emitter is stopped. Let's explore one of the simplest logic configurations that uses just one transistor, and then we'll build it on a breadboard to see how it works. Now, if this is your first time seeing a digital schematic like this, there's a few things you need to know. First of all, you might already know that a circuit must be a closed loop in order to operate. These 5-volt and ground markings imply that somewhere there's a power supply like a battery that raises this 0 volts back up to 5. Similarly, inputs and outputs need to be connected in order to work, but we're only concerned about the logic of this part of the circuit, so we'll assume something is supplying the input and something else is receiving the output. Also note that because the supply is 5 volts, that is the high level. In this case, 5 volts represents a 1 in binary. And then of course, 0 volts, or ground, represents a 0 in binary. This concludes stuff you need to know about schematics, so let's get back to the transistor operation. If we provide 0 volts to the input, electricity is not allowed to flow from the collector to the emitter. Because of this, it's as if the transistor is disconnected from the rest of the circuit. Current then flows through the resistor to the output. Remember, because the output is 5 volts, it's considered high, or binary 1. So when we provide a 0 to the input, we get a 1 at the output. Let's record that in this table, call it a truth table, and see what happens when we provide a 1 instead of a 0 at the input. Because the voltage at the base is higher than the voltage at the emitter, electricity now flows into the base, turning the transistor on. Electricity can now flow from the collector to the emitter, and it will. Because the transistor now connects the output node to ground, it forces the output to be low. In other words, when the transistor is on, the output is ground. This resistor is here because it provides a default of 5 volts to the output if nothing is done with it. Because of this, we call it a pull-up resistor. So when the transistor is off, the resistor passes 5 volts, but when the transistor is on, the resistor, in a way, disconnects 5 volts from the output because it's grounded. Let's record that in the truth table. As we can now see, the truth table provides a summary of the behavior of the circuit depending on the input. When the input is 0, the output is 1, and when the input is 1, the output is 0. We've created an inverter. And now for the fun part. Let's build this on a breadboard. So here I have a transistor. You can see it has a flat side and a rounded side, so you know which pin is which. I'm holding the emitter currently, and the collector is on the other side. Well, the base is generally in the middle. So I'm going to connect the emitter to ground, which is this black rail at the bottom. And I actually have a modified transistor with the pins already bent how I want them. And then of course the collector gets connected to 5 volts through a 220 ohm resistor. And then we need the input and output circuitry. I already have a yellow wire here, which represents the output, and we can see the output with an LED. So when the LED is on, that means a 1 is being output, and when the LED is off, the output node is grounded, which is a 0. And then to control the input, I have a regular button here. So I'll connect that to the base and to 5 volts as well, again through a resistor, which we didn't talk about, but that's so that we don't damage the transistors. So now the input is connected to 5 volts through a resistor and through a button. And when the button is pressed, we're providing a 1, and when the button is not pressed, we're providing a 0 to the input. And all we need is power. So here I have a barrel jack, which I'll plug in a moment. And if I plug in the barrel jack, you can see that the LED is on by default, which we would expect because I'm providing a 0 to the input. But when I provide a 1 to the input, the LED turns off. So the output is always the opposite of the input. This is probably the simplest logic device there is. Now, we don't want to look at the individual components of the inverter if we already know how it works. So let's simplify it. This is the logic symbol for an inverter. This bubble may appear on many other components as well, and it simply represents the inversion of the signal. The arrow represents the direction of the signal. And it works just the same as before. Now, it's pretty neat that we're able to make this whole circuit into its own symbol. This is called abstraction, and it's a very important concept of computer engineering. By simplifying the circuit, we moved up one level of abstraction, from the transistor level to the logic level. Of course, we can use abstraction in hardware as well. This chip is called the 74LS04, and it has 6 inverters inside of it. The only pins I'm using on this chip are this input where the white wire ends and this output where the LED is. Those are the only 2 pins I'm using, except for, of course, the providing power to the chip. And other than that, all I have is the input circuitry with the button and the output, so we can see it with the LED. And it works just as expected. Now I know things are getting pretty complicated pretty quickly, but there are only a handful of other logic gates. As a matter of fact, we're going to go over all of the remaining 1 and 2 input logic gates in the next video, so stay tuned.